Okay, so yeah, great. So as I said, I'll be talking about uniformly convex spaces, and here the example is the Hilbert space or the Euclidean vector space. I'll take just R2 because really when you look at the definition of uniformly convex spaces, is a two-dimensional definition in any case. So here let's continue. So we have the norm of U plus V over squared plus the norm of U minus V squared is equal to 2 norm of U squared plus 2 norm of V squared. This is the parallelogram identity, okay, in the Hilbert space. And if we now, from this identity, we see that if the norm of U is less than 1, the norm of V is less than 1, and the norm of U minus V is greater than epsilon, so it's far, U and V are a little bit far from each other, then we have the norm of U plus V squared. This is less or equal 2 plus 2 minus epsilon squared. Okay? And this will give me 4 minus epsilon squared. Or the norm of U plus V is less than square root 4 minus epsilon squared. Okay? And from here you get, if you divide by 2, norm of U plus V over 2 is less or equal than square root of 1 minus epsilon squared over 4. So what does it mean? It means that if you take the unit ball and you take U, V, okay, and you take the middle one, so you get here, and you take the middle one, this is the middle one, U plus V over 2, then this middle point is inside the ball, okay, so it's inside. But the distance, how far you are from the sphere, is measured, let's say we measure it by delta of epsilon. And that delta of epsilon can be measured. In this case, for example, we can show that this is less than 1, and the delta epsilon, in fact, can be taken to be 1 minus square root 1 minus epsilon squared over 4. How far you are from 1, okay? So this delta epsilon is positive, okay? Or can be taken anyway. So there is another definition for delta epsilon. Delta epsilon, we can write it as the infimum of 1 minus norm of U plus V over 2, such that norm of U is less than 1, norm of V is less than 1, and the norm of U minus V is greater than epsilon. Okay? So this is all in R2. Okay? This is coming from the Euclidean Hilbert space R2. Okay. So the people wanted, so first of all, since norm of U and norm of V are less or equal than 1, epsilon must be less than 2. Okay? Number 1. Okay? And number 2, delta epsilon, it's very easy to see that delta epsilon is going to be less positive, okay, positive, and less or equal than 1, okay, all the time. So here the people wanted to extend this property, so they extend its definition. Okay, same properties we have in the Hilbert space. And again, this property in R2, because it involves only these two vectors, but you can see here that delta epsilon has nothing to do with the two vectors U and V. It's equal to 1 minus square root of 4 minus epsilon squared over 4. So even in infinite Hilbert spaces, we have the same inequality. So it's really, so let X be a normed vector space. Okay, and for minus Cj when I and j are greater than n. Okay? So the dn's are basically they are decreasing. Okay? So here we have dn plus 1 is less than dn. And we want the limit of the dn's to be equal to 0, which means basically that the sequence Cn is Cauchy, but assume not, so limit of the dn's equal the infimum of the dn's is not equal to 0. Okay, so this is very important because I'll be using a lot what we call the asymptotic diameter of the sequence. Right? It has a name in metric spaces. Okay, so here let's set this number to be d. Okay, so d is the limit of the dn's. Okay, so now what do we have? We have for any n greater than 1, there exists in gn greater than n such that the norm of Cin Cgn is greater than dn over 2, because dn is positive, so, and dn is the soup. If you take dn minus any positive number, then you can find an element that is bigger than the soup. Huh? So in fact we can even put here strict. Okay, but the dn's are bigger than d, so this will be greater than d over 2. So it does not depend on what? On n. Okay, so now we take epsilon to be d over 2 times the distance from x to c plus 1. Okay, this is positive. Okay, now take v u equals x minus Cin over the distance of x to c plus 1 over n, and v equal x minus Cgn over dxc plus 1 over n. Okay? So what's the norm of u? Norm of u is the norm of x minus Cin over the distance from x to c plus 1 over n, which is less than the distance x minus Cn is less than the distance from x to c plus 1 over n. Okay? So here this will be x to c plus 1 over in over distance from x to c plus 1 over n. And since in is bigger than n, 1 over in is smaller than 1 over n, and therefore this is less than 1. The same holds for v. Okay? And if we take norm of u minus v, we're going to find norm of Cin Cgn over distance from x to Cn plus 1 over n to c. Okay? And our definition of Cin, so we said this is greater than, right? See how we got it? Cin minus Cgn is greater than d over 2. So this will give me, this is d over d over din dxc plus 1 over n, but plus 1 over n is greater than 1. Okay? So this tells me that 1 minus delta x of epsilon. Okay, so since we are uniformly convex, so you get dxc is less than dxc contradiction. Okay, so this will imply that contradiction, and therefore we have what? We have that xn is Cauchy. Cn is Cauchy, not xn. Now we use the fact that it is Banach, so x is, since x is a Banach space, then limit of the Cn's equal to C when n goes to infinity exists in C. And it's very easy to see that the norm of x minus C in fact is equal to the distance from x to C, so we do have a best approximate. Okay, so the same proof, it's very easy to see that you cannot have two of them. This is what we call strict convexity. And it's very, very easy to see that if you have the norm of x minus C1 equals the norm of x minus C2 equals the distance from x to C, then C1 is equal to C2. Assume not, and then use the uniform convexity, and you will find that C1 plus C2 over 2 is going to be, it's going to give you a distance from x to C that is smaller than dxc. So it's very, very straightforward. Okay. Then in this case, we have proved that there is this map from x into C such that you have the best approximate. Okay, this best approximate in fact is continuous, but it doesn't have nice properties. Only in the Hilbert space, if you look at in the Hilbert space, that PC, okay, is what we call non-expansive. It has Lipschitz constant 1. Okay, is Lipschitzian with constant 1. Okay, but in general, that's not true in any Banach spaces. That's absolutely not true. It is continuous, but it may not be Lipschitzian with constant 1. Okay, and also if you assume that C is a closed subspace, if C is a closed subspace of X, there is no reason for PC to be linear. It is true in the case of Hilbert again. Okay, that PC is linear, is even orthogonal. But anyway, this is not true in general Banach spaces. Okay, in general Banach spaces. Okay, so this is property number 1. Okay, so the proximality. Property number 2 is very beautiful. Property number 2. Okay, this is nice. So you take let X be uniformly convex Banach space. Okay, and you take uniformly convex Banach space. Then for any Cn, okay, bounded sequence of convex closed non-empty subsets of X, such that here we assume decreasing, such that Cn plus 1 is smaller than Cn. Okay, so it's decreasing sequence. Then the intersection of the Cn's is not empty. Now we're getting somewhere. Because, let me just say something. This is interesting now. Now things are getting interesting. Why? Because if you take a convex set, what is convex? Convex means it's a linearity property. Okay, so it's the linear algebra here. So it doesn't matter on the norm to be convex. And to be closed, non-empty, that's obvious. But to be closed and x minus Cin divided by dx, v equal x minus Cgn divided by d of x. Then what do we have? We have the norm of u, norm of x minus Cin over dx, and this is the distance from x to Cin over d of x. Okay, and all the distances are less than dx. Dx is the supremum, so this is less than 1, and the same holds for the norm of v as well. Good. So now let's go to the norm and norm of u minus v. So this will be is going to be the norm of Cin minus Cgn divided by dx, and this is greater than what? Din is greater than dn over 2 times dx, which is greater than d over 2 of dx, and that's epsilon. So the norm of u plus v over 2 is going to be less than 1 minus delta x of epsilon. Okay? And it's very easy to see that the norm of x minus xin c plus cgn over 2, and remember it's divided by dx, 1 over dx, this is less or equal than 1 minus delta x of epsilon, which gives me that the norm of x minus Cin plus Cgn over 2 is less or equal than dx times 1 minus delta x of epsilon. Great. So now Cin, Cgn are all in Cn. So this is, Cn is convex. So we get that the distance of x to Cn is less or equal than dx 1 minus delta x of epsilon. And this is true for every n. So in particular, if I take the supremum, okay, the supremum, I'm going to get that the distance, supremum of this, dx is less than dx times 1 minus delta x of epsilon, okay, and this is a contradiction. Okay, therefore, Cn, so the Cn's are Cauchy, is Cauchy. Okay, since x is a Banach space, then limit of the Cn's when n goes to infinity equals to C belongs to x. Great. But now what happened is that since the capital Cn, the closed sequence of closed convex sets is decreasing and closed, then you see, starting from Cn, Cn plus 1, Cn plus 2, they all belong to capital Cn, therefore the little c will belong to capital Cn for every n. Okay? So since they are closed and decreasing, since Cn's are closed and decreasing, then C belongs to Cn for every n greater than 1, which means that the intersection is not empty. So the intersection of the Cn's is not empty. Okay, so this shows that we have this property, and I called it property R. Okay, so here the property, this definition. Okay, so this intersection property, of the convex sets is called R. I called it R in 1987, okay, for the first time. We know that in Banach spaces, if you have this intersection property, then you are reflexive. It's a beautiful result, okay?